So, okay, so since gate exam is near, I was thinking more of a revision kind of a session. So, I was thinking I will take gate questions in every session, or you can also mail me gate questions which you are doubtful about, but please adhere to the subject, which is analog electronics. Okay. Um, I am not a devices person, so for electronic devices, I might explain you the question, explain you the solution, but I may not be able to go very deep into it. Okay, so you can give electronic devices questions as well, but very deep explanations I may not be able to give you, but I'll give you the conceptual explanation for those kind of questions. And any other suggestions you can tell me if you want anything else to be done in this weekly course, because it's a very short time, 1 hour only. So I was thinking it will be better to go with solving problem solving kind of approach so that you guys have a revision kind of thing. So since people are joining still, I'll wait for 1 more minute and then we can start with this question, which came in GATE 2015 set 2, and it's related to Schmidt trigger concept. Okay, so you can read the question by that time. So when I solved this question, after that I was just checking the Schmidt trigger concept in online. So I just googled Schmidt trigger using Opamp, like that I googled and I found some links. Okay, and I was astonished to see that the inverting Schmidt trigger concept is very well explained. Okay, but the non-inverting the explanation they have done correctly, but the equations they have written wrong. Okay, and I was quite astonished as to how they can provide such wrong information regarding a important topic. And I saw there are many YouTube videos also who have done wrong explanations to it. And the reason is that they are just taking a formula and saying that, okay, this is the formula, this has to be the case. They are not deriving the formula. So today I'll give you the overview of the Schmidt trigger. Okay, how it is, what is the difference between non-inverting Schmidt trigger, inverting Schmidt trigger, and what is wrong where they are putting the wrong information. That also I'll tell you. So I did find one of videos I found which was actually he was solving it correctly. So I'm not saying that everybody is solving it wrong. Okay, so but I think this is a point where people can do mistakes. Okay, so we need to take care of that. So, okay, then I will start with the problem. So this came in GATE 2015 set 2. Okay, and it's mentioned that it's a bistable circuit. Okay, that is, it is having two stable states. Okay, so bistable circuit is also known as like normal oscillator circuit. Okay, the ideal op-amp has saturation levels of plus minus 5 volts. The value of R1 that gives the hysteresis width of 500 millivolts. So what is hysteresis width? What is saturation levels? I will give you a quick overview of op-amp first. Okay, since I don't know how many of you know the conceptual part of op-amp, so I will directly give you a short overview of op-amp. Okay, so what normally we see an op-amp in questions is this. Okay, so you know this is non-inverting terminal. I am writing an IV, an inverting terminal IV. Okay, and it has a supply of plus VCC, minus VCC. These are called dual supply op-amps. This is a dual supply op-amp. Okay, and you also have single supply op-amps as well. So I'll give that also what it is. So dual supply op-amp, you have the voltage rail is from plus VCC to minus VCC. Okay, and if you consider an ideal op-amp, that is the open loop gain is infinity. Okay, so in such a case, what happens is that okay, and there is this output V out. Okay, okay. So now when an op-amp with infinite gain is there, that means it's an ideal op-amp. Now the normal configuration that we normally see is something like this, that either the input is here and you have a circuit like this, right? You would have seen this one, this you would have seen, right? And another type you would have seen, which is right. These two you would have seen. Okay, so what is the difference between these two? In first, I am putting the input in non-inverting terminal. In the second one, I am putting the input to the inverting terminal. But the feedback in both the case, so feedback means feedback. You take a portion of the output and you feed it back with the input. Okay, so there is a portion of the output you take and you feed it back to the input. The feedback, when it goes to the negative terminal, so you can see in both the cases the feedback is going to the negative terminal, right? This from here also the signal is coming and entering the negative terminal. From here also the signal is coming and entering to the negative terminal. The difference is that the input is applied to in one case non-inverting, in another case inverting, right? So in this case these are both negative feedback. These are both negative feedback. Okay, always in negative feedback, what is happening? Negative feedback means you take a portion of the output, let's say K times V out. You take the portion of the output and you subtract it with the input. Okay, you take a portion of the output and you subtract it with the input so that you get an error which you try to minimize. So the work of negative feedback is minimizing this error so that ultimately this error tends to zero. Okay, so the work of such a circuit, the work of negative feedback is, the basic concept is that we get a V error and we try to minimize it. Okay, so this is how what happens in the negative feedback. Okay, now the other type of feedback will be the positive feedback, where you take the value and you add it up. so that now the V error is not going to 0, but the voltage is actually trying to increase. Okay, and therefore in that kind of a circuit, even if you remove the Vin, it doesn't matter, the circuit will drive itself. Okay, and that is what the concept of positive feedback or oscillator is. And therefore they are also called regenerative feedback, because you are regenerating the input. Even if you remove the input, the small output which was earlier generated, it can function itself, it will treat itself as the input and it will keep on increasing. So that is a positive feedback. So this is a positive feedback. Remember all other configurations that the Opamp has, as a buffer, okay, or as inverting amplifier, buffer, all these are negative feedback configurations. Okay, positive feedback is means whenever you want to do either a comparison or a regeneration, there you use, or an oscillation, basically there you use positive feedback. Okay, so if I have a configuration like this, here you can see the feedback comes to the positive terminal, right? Here you cannot apply virtual ground, right? So you cannot say that this terminal is 0 volts, so this is 0 volts. No, it is not. Okay, because the concept which was actually trying to make it 0 volts was the negative feedback, which was making the error 0. So this is not true. So how we solve these things then? So here here I'm assuming that you already know this circuits solving, which is basically very easy. It is nothing but network, right? So here you know that whatever voltage is here, this will be the same as Vn, right? This is also Vn because of virtual ground concept. So virtual ground concept applies here, right? And from here we get, for a non-inverting input, we get V out as 1 plus Rf by R into Vn, and for an inverting thing we get V out as minus of Rf by R into Vn. The only difference is this negative sign. So basically it inverts, and in non-inverting terminal it does not invert, right? So otherwise the feedback is always negative. It is not that in non-inverting the feedback is positive. No. If the feedback is positive, it is not an amplifier, it is an oscillator. Okay. Now, the same happens with BJTs as well, with MOSFETs as well. So any circuit, if you want to generate, so this you will again study, I think, in networks as well as control system, that the RLC circuits, if you remember, that we used to study, LC oscillator, Colpitts oscillator, everything is positive feedback. Okay. Negative feedback means amplification. Okay. Now, with this small amount of conceptual knowledge, we go to the positive feedback concept. Okay. So now you see I am putting the input in the non-inverting terminal, and there is, okay, so there is this circuit. So if virtual ground is not applied, then what can I do? So in this case now, this is a V. I'm just applying V here. Like I'm just assuming a voltage at this node V. Now what the op-amp will do? Op-amp is nothing but an error amplifier. Its job is to compare its two inputs, and it tries to take it to 0. Okay, so it basically compares the two inputs, or you can say it subtracts the two inputs. Okay, whatever the difference is there. So now what will happen? It will compare V, since this is 0 volts ground, it will compare V with 0. So either V is greater than 0 or V is less than 0. Okay, so now what happens? If V is greater than 0, okay, what will happen? It will take V non-inverting terminal minus V inverting terminal. It will multiply it with the open loop gain, and that is your V out. Okay, so now V in non-inverting is what? V non-inverting is V, right? You can see I have pointed it out, V. Inverting is what? The inverting terminal is what? It is 0. AOL is what? For an ideal op-amp? Infinity. This equals to V out. So now can V out be infinity? Can it show infinity? If I connect this node to an oscilloscope, what will I see? Will I see infinity? I cannot see infinity, right? What will it come? This is the case where we say that the op-amp saturates. So to denote this, what op-amp does, op-amp gives you either a plus VCC, which is its supply rail. It cannot go beyond that. Okay, it cannot go beyond that. It is like you are making tea and suppose you have a 2 teaspoon of sugar you are having. So you cannot put more than 2 teaspoons, right? Even if I want 3 teaspoons, you cannot give me 3 teaspoons because you are having 2 teaspoons. You cannot give me more than that. So since the op-amp is having power supply plus VCC and minus VCC, it saturates to those levels. Okay. So what will happen? If your non-inverting terminal, V non-inverting, is greater than V inverting, the output is plus VCC or plus V sat, whatever is the case. And if your terminal is less than V inverting, then V out is minus VCC or minus V sat. Okay, and I think this is a very basic thing, but some people get confused between this sign. Arrow idhar hoga ki idhar hoga, they keep on asking which side the arrow will be. So whichever side the arrow opens is the greater side. Okay, so if I say X is greater than Y, so the arrow is opening here, right? So this one is greater, X is greater. Okay, so anyways, so now plus VCC or my this you understood, right? How comparison works. So now let us again start. Normally in gate, inverting op-amp Schmidt trigger used to come. Okay, normally inverting op-amp Schmidt trigger used to come. So, but in 15 they gave a non-inverting Schmidt trigger. So this is V in, this is R1, this is R2. Now what will happen? What will you do? Now you know that this is the voltage to be compared, right? V is the voltage to be compared. So let me write a normal KCL equation. So V minus Vin by R1 plus V minus V out by R2 equals to 0. Remember, V is not equal to 0. Virtual ground concept not present. Virtual ground concept not applicable because it is a positive feedback. Right? Positive feedback. So now what will happen? V, you solve it, you will get V as R1 by R1 plus R2 into Vn plus R2 here R2 and here R1. R1 plus R2 into V. This can also be easily solved with the superposition theorem as well. Okay, whatever you want to solve from network concept, you solve it and you get V. Now this V is to be compared to 0, right? So now this V will be compared to 0. So if V is greater than 0, the output will be plus V sat. Okay, and if V is less than 0, the output will be minus V sat. Right? So now what will happen? So that means V equal to 0 is the point of transition. Right? So then if I put it like that, then we define two voltages, which is called upper threshold VUT and lower threshold VLT. So whenever the input is equal to VUT, after that the V out becomes plus V sat. So that means V greater than VUT gives you V out plus V sat. And V less than, this is V in less than VLT will give you minus V sat. So remember, the upper threshold and lower threshold are the values of the input voltage. And plus Vset minus Vset is the output voltage. The op-amp will only compare what comes into its terminal. The op-amp will only compare these two voltage, right? Now, if I have some circuit, some very big circuits I'm having, okay, and then I am putting so the input is here. I'm putting it into a black box. I'm having a feedback here. And then I'm saying, okay, what will be the output? So op-amp will only compare this voltage, right? V1, V2. Op-amp will only compare V1, V2. So what is V1 is from, I'm trying to derive from Vn, because Vn is my actual input. So if I want to see this, the experimental setup, how it will be. I have a function generator that generates Vn, and then I have all this big circuit, and then I have an op-amp which works as a comparator, and I see the output in oscilloscope, right? So here also the same thing is happening. They are putting the input Vn with the help of a circuit which also works as in a feedback manner, so that this works as a Schmidt trigger. And this kind of circuits are normally used to convert the input to a square wave generation, because the output always switches between plus VCC and minus VCC. So we will see how square wave comes. Okay. So what I mean to say is that when Vn's value, so if I now try to do a graph, so if Vn's value is VLT and VUT, okay, and if anything goes above this is Vn. So if Vn goes above VUT, it is plus VCC. And if Vn goes below LT, it is minus VCC. Okay, and then you get this kind of a curve. The arrow here is wrong. So you get this kind of a curve. Okay, and this is called a hysteresis curve. Okay, so I will not go into the hysteresis curve and all those things. I just wanted to show you a hysteresis thing that is happening. Well, I'll come to the main point. So now again, this was our circuit. We found V. We saw that it is being compared to ground. V is greater than 0 or V is less than 0. Remember, this can be any voltage. I have connected it to ground. It can be any voltage. In that case, your equations will change accordingly. Okay. So now we have found that V is equals to V in into R2 by R1 plus R2 plus V out into R1 by R1 plus R2. This we saw, right? So now since V is being compared to 0, what will happen? V in will be either less than or greater than what? V out into R1 by R1 plus R2. This one, right? Same here. So either greater or less. So other stuff cancels out. So V in is compared to directly, if you can see, it is compared to R1 by R2, right? So you see the op-amp will compare these two voltages, V and 0. This is what it will compare. But we only know V in and V out because we are giving V in from a function generator. So I know V in and I'm seeing V out because it is coming in the oscilloscope. I don't know what is going in between. That is not in my control, right? So in terms of V in and V out, this is what is happening. Now there are again two other variables. What are they? We saw that V in can take two values. One is the upper threshold value UTP and another is the lower threshold value ULTP. And V out will again take two values, plus VCC or minus VCC. Now whenever V in is taking VUTP, so V in is let's say it is VUTP. So we saw that it will come out to be what? V plus VSAT, right? So then VUTP is nothing but plus VSAT into R1 by R2. Okay, and then VLTP will be nothing but minus VSAT into R1 by R2. And the width of hysteresis VH is defined as VUTP minus VLTP, and that is nothing but 2 VSAT into R1 by R2. Okay, and in the question this value is given. This value is given 20k, and they are asking what will be the value of R1. So here what will happen? They have given VH as well. They have given the width of hysteresis, which is 0.5 volts. They have given VSAT value, which is 5 volts. They have given R1 as R1. They are asking, and R2 is 20k. So you can see R1 value is 1 kilo. This was the answer. Now this is what happens in a non-inverting Schmidt trigger. So non-inverting Schmidt trigger means the input goes to the non-inverting terminal and there is a positive feedback. So let me write it down. Non-inverting Schmidt trigger, positive feedback, input goes to non-inverting. So when I say input goes to non-inverting, it doesn't mean that I directly connect it. I can connect it in any way. This doesn't mean this, necessarily does not mean this. It can be connected in any fashion, right? It can be connected with a series of resistors like this. So it can be like this as well. Let's say something like this, okay? But what I mean is basically the feedback is positive. So what you will see is this kind of a circuit only, because this is what will give you proper output. Okay, now the other circuit is inverting Schmidt trigger. So I'll go over that only. So non-inverting Schmidt trigger, this output, okay, this equation that we came up with, this is what I was talking about, that this is what I did not see in the websites I was going through, and they have not worked out this equation. Okay, they have worked out the same inverting Schmidt trigger equation, okay, which is not the correct one. So now let's see the inverting Schmidt trigger. Okay, so in inverting Schmidt trigger, what happens? Feedback is still positive. But the input is now applied to the inverting terminal. Now in this case, what will happen? So V by R1 so what you are having? So this is a pretty simpler thing to understand. Okay, so what was difficult to understand is what I already explained. This is pretty simple. What are we doing? We are getting some V out and we are just feeding it back to this terminal. And whatever is coming, we are simply comparing it with V in. So when you solve this KCL equation, you actually get what is being fed back. So V is what is being fed back, right? V is here. So V is what is being fed back. So what is being fed back is V out into R1 by R1 plus R2. And that is what you compare. So you compare V into V out into R1 by R1 plus R2. Now the same thing. Now you see V in is in the inverting terminal. That means whenever Vin is greater than this fed back voltage, whenever Vin is greater than this fed back voltage, let's say V, the output has to be negative, minus Vset, right? And whenever Vin is less than V, Vout is plus Vset. And this will define your upper threshold VUTP. This defines your VLTP. Okay, and the VH is given by 2 times R1 by R1 plus R2 to Vout. So you have to be careful if question comes. Okay, if it is asking for inverting configuration, if it is giving the input to inverting and the positive feedback is there, you have to solve in this way. If it is positive feedback and input is to the non-inverting terminal, you have to solve it the earlier way. Okay, I hope you are getting my point here. Okay, so now how it turns out to be a square wave, let's see. So suppose I am taking a non-inverting one only. This is the sine wave I applied. Okay, and this is VUTP, this is VLTP. So VUTP is somewhere here, VLTP is somewhere here. It's just a voltage, right? It has to be a constant voltage. So now this is your Vn. This is T with respect to time. Now what will happen? This is VUTP. Here also it crosses VUTP. Here it crosses VLTP for the first time. Here it crosses VLTP for the second time. Here it again crosses VUTP. Okay. So what will happen? We saw that when this input is less than VUTP, the input went to the non-inverting terminal. Okay. And input is less, so the output will be minus VCC. Now when the input has started growing more than VUTP, right? You see the VUTP is this constant line, right? So when the input has more than VUTP, it has to be plus VCC. And here it does not matter. Here if you see, it will still continue to be plus VTT. Okay, until it comes to LTP, because LTP is what the voltage which is actually throwing it inside, throwing it to minus VCC. So as soon as it encounters LTP, it goes to minus VCC. And it will continue to minus VCC until it again encounters VUTP, which actually throws it to plus VCC. Okay, so basically our starting point is VUTP. This is our starting point. So whatever happens before this, you ignore here. Okay, so after this is how the circuit will continue to behave. And therefore, when you apply a sine wave, you get a square wave. So regenerating circuits are always like, they are mainly used for square wave generation. And after that, if you use an integrator, you can generate a triangular wave. This we normally study in communication also. Okay, square wave and triangular wave, how things are coming. So this was the entire concept of this question. I think this was a 2 marks question. Okay, if you know the formula, it's pretty simple. But how did you get that formula? Okay, and that formula will not exactly, I don't know, I have not solved it, but that this formula thing, it may not work if you have some other kind of configuration. Suppose you have some other voltage to compare with. So let's say you have V comp here and you have V in here and this is V. So now what you are comparing is, what you will be comparing is not ground but a voltage which is already there. So V greater than or less than V comp is what you have to do. You understand? So earlier I had made V comp as 0. So then you are comparing with 0. But now if there is V comp, that particular voltage will come into picture. Okay, suppose I say V comp is 1 volt. So now whatever equation you will write, so V minus V in by R1 plus V minus V out by R2 will now be compared with, not equal to, compared with 1 volt. Okay, instead of 0, it will now be compared with 1 volt. Okay, and when I made it 0, so you may have this doubt that why did you make it equal in this case? Like for trying to find out when I'm saying V in is greater than or equal or less than, and then I just wrote this equation which basically says that it is equal to, okay. So because this is the hysteresis curve we are talking about, okay, we are now not talking about, so we are actually at the transition point, that's why we are using the equal sign, okay. So this was the entire solution. I hope this solution is you have understood. So if there is any doubt, you can ask me. So after that I'll go to the second question, so just 2 minutes I'm giving you just to ponder upon. So the next question is from GATE 2022. This is a very simple question, okay. There is nothing more to it except that you should know the concept of Bode plot, okay. So that which you will be studying in I think in control systems you will be studying Bode plots, and it's very important for you to know that. So this I had mentioned earlier also in the videos, that in the live session that I had taken that it's in the paper it is not that only analog electronics questions will come, they will mix and match. So you will have to use network, signal, analog and control, four subjects together in one question, and that can only happen if you have the conceptual clarity over all these subjects, okay. So this is a very simple question. What is given is the output voltage Bode plot, okay. So this is the output voltage Bode plot, voltage gains Bode plot, okay. And from here what you can get, directly the gains value, right. So now if you know how to plot Bode plots, which I will not go here, 20 log A is nothing but 12, and therefore A's value will be, what will be A's value? 10 to the power 12 divided by 20, which is nothing but 3.98, that is equal to 4, right. So now I have got the gain, which is a closed loop gain, right. I've got the closed loop gain here because the op amp is in feedback, and you see it is a negative feedback, right. It is a negative feedback, okay. So now since the feedback is negative and I have this kind of a circuit, what they are asking is the values of R and C. So what will define this closed loop gain? This will define the closed loop gain, right. This in the inverting terminal, whatever feedback is there, that is going to define the closed loop gain, right. So but the input is in which terminal? V in. So this is which configuration? Non-inverting, right. So since the input is applied to the non-inverting terminal, to the positive terminal, the gain is what? Right? This is the gain. You can see. So the input is here applied to the positive terminal. There we zoom. Okay. So the input is applied to the positive terminal. This is the input here. Right? So if you solve, now what you will start doing? That okay, there is an R and there is a C and I will have to apply KCL across the cap also. No, you need not do anything. Okay, you did not do anything like that here. Why? So at DC what will happen? The gain which comes is basically the DC gain we talk about, right? So when at DC what happens? Capacitor will be open circuit. So this is an open circuit point here. And if this is an open circuit point, then the Vin, there is no current pushing here. Therefore, this Vin is nothing but this Vin because there is zero current from here. Okay, Opamp's terminal anyways the current is zero, right? So Opamp terminal inside current cannot go. So this is zero. This one is also zero. So I think it is 2. Yeah. So at DC, whenever we talk about gain, whenever we talk about closed loop gain, we actually talk about DC. So at DC, what will happen? Capacitor will be open circuit 1 by 2 pi FC, right? So F is 0, capacitor is open circuit, infinity. So this is open circuit. So there is no current passing here. Input of the op-amp is 0. Okay. Input of the op-amp is 0. This is also 0. So there is 0 current. As the frequency increases, after that something will happen. Okay. But at DC what will happen? The Vin is here. So if the Vin is here, then this circuit is nothing but similar to this circuit. Right? And what for this circuit, what is the formula? 1 plus RF by R. That's it. So 1 plus RF by R is nothing but 4. From where 4 came? From the Bode plot. Okay. You can see here in the axis itself they have given 20 log A. So even if you don't know Bode plot, you know this is the value of 20 log A. And you take 20 log A, you get it to 12, you get A is equals to 4. So now R is given as 1K. So 1 plus RF by 1K equals to 4 and RF is nothing but 3 kilo ohms. So one of the values I got. RF is 3 kilo ohms. Now, next they have asked, what is the value of C? So now there is a frequency here as well. Right? There is a frequency here as well. And how will you understand what the frequency is? So you now have to see the cutoff frequency. So again come to the Bode plot. So this was a very good question, interesting question. If you know how to read up Bode plots, you will be able to solve this. So what they have done, they have given you 12 volts here, right? But they have not mentioned anything else. You have to find it out. So since this was constant at 12 volts, I know this is my closed loop gain, the DC gain. Okay. Now, we know cutoff frequency is nothing but 3 dB frequency. 3 dB means from the DC gain you go 3 dB down. From the DC if you go 3 dB down you come at 9. And at 9 what is the number written? 3. Right? So this is nothing but 3 dB down. So at 3 dB down when you go, that frequency is nothing but 3 dB or cutoff frequency. And cutoff frequency is something which is decided by whatever components you have put in your circuit, the R and C. So now this 3 is nothing but what? Log 10 omega. That also they have mentioned. So log 10 omega is nothing but 3. This means omega is nothing but 10 to the power 3, which is nothing but 1000 radian per second. Right? And they have asked you value of C. So what is this omega being decided by? By this circuit. That is why it is there. Okay, this is a low pass filter circuit. That is why it is there. So it is used with op-amp so that there is a buffering action that is happening, the loading does not happen. Okay, that is why we use Opamp. The loading stops. Okay, so now what you will do, R is 1K into C equal to 10 to the power 3 radians. Okay, and therefore I had done something wrong. Yeah, so 1 by RC. So 1 by RC is nothing but 10 to the power 3, and therefore C is nothing but 1 microfarad. You can check. So this was the entire concept behind this question. Okay, so you need to understand the Bode plot. That's it. For solving this question, if you have a knowledge of Bode plot, you will be able to do it. The answer was option A. So the answer is not important, okay, when you are solving. When you are solving, what is important is whether you are able to catch the problem, whether you are able to understand what is given to you. Okay, so I hope these two problems were clear. So you can now see how the solutions have gone. And if you are in any doubt, you can ask me. After that, I will quickly go through one more concept and then we'll wrap it up. Okay, so I hope this is done and you have noted it down. Again, like last time, I will be uploading these live videos in my YouTube channel, but I will not do it now. I will do it after some time. Okay, once the Gate NPTEL team gives me the permission, I will do that. Okay, so okay, so there is one concept of Opamp that you should remember, that I was mentioning that it can be a dual supply Opamp. Okay, in this case, the power supply is plus VCC minus VCC. Okay, and you have whatever input output, whatever you want to do, you can have, and there is the output. Okay, right? So now in this kind of Opamp, if I ask you to work in a inverting fashion, so I'm saying, you know what, you use it as an inverting amplifier. I'm saying, okay, I'm saying, okay, I'm giving you a voltage V in, you just try to give me a negative of it. Okay, so I'll give you a V in as input. What I want at output is minus V in. Okay, so how will you use this Opamp? If I say this, you will simply take this Opamp. Let me draw it a better way. So you will take this Opamp, right? And what will you do? If I say that you have input and you need to get an output which is just the inverse, you will simply do this, right? This is 1K, this is 1K, this is input V in, this is V out, right? So what you will get V out as minus of RF by R1, which is 1, so you get V in. This is clear to everybody, right? Okay, okay, great. This will only happen if you have the rails as plus VCC to minus VCC. Why? Because we had seen that the Opamp will take whatever its value is in the rails. So if my rail goes from minus VCC minus 5 volts to plus 5 volts, this is what my Vin will be restricted to. So if the Vin is going negative, I should have that room for negative voltage. So the voltage will now come here. So this ground which I connect to it is nothing but a reference. Okay. So now if I have a single supply Opamp, please understand this. If I have a single supply, then what will happen? This goes from plus VCC, 0 volts. So all the power rails it has is positive. So it cannot take any negative values, right? So in this case, what happens? How will you achieve a inverting amplifier? right? What will you do to the negative terminal? Will you connect to ground? No. This will now be connected to VCC by 2. And whatever is now the output, okay, whatever is now the output from VCC by 2 to VCC, it will be taken as positive. From VCC by 2 to 0 volts, it is taken as negative. Because now the reference is VCC by 2. Okay, so if you want the exact inverting thing to come, then you need to use a dual supply op-amp. Or what you can do, you can use a single supply op-amp and then you can level shift it again. Okay, then you will have to level shift the entire thing by VCC by 2. So ground, the concept of ground is always with respect to something. So right now my ground is nothing but VCC by 2. It is not 0 volts, it is some other volts. So please remember this concept. These kind of concepts can be given in GATE exam, okay, because this is where people kind of do mistakes. So these kind of concepts can definitely be shown in GATE paper. Okay, so always check whatever they have given in the supply rails, what is there. Just don't blindly, if you are sorry, here I have done one mistake. This is minus, this is plus. I had made a positive feedback. That is minus, this is plus. Okay, so don't just blindly do the question. Look at the question, understand it. It is not that you just saw a question, you saw, okay, this is inverting amplifier, input to inverting terminal, and negative feedback. Okay, blindly RF by R1. That's it. No, that is not going to happen. You have to see the power supply range as well. If it is going from minus VCC to plus VCC, what you are doing is correct. If it is not going, you need to check it once. Then in the circuit itself, they will not connect that to 0 volts. If they do it, your output will not be correct. Okay. Okay. So with this, I will end up today's session. Any doubt in whatever we did, and what you will like to do in the next session? Do you want me to continue solving problems, or what you want? Any suggestion is welcome. We can discuss that. Anyone? Okay, so I'll mention my email ID as well, so that if you want, you can send me any problems. Okay. Oh, sorry, I did not introduce myself. That I should have done right in the beginning. A few of you have joined earlier also in the live get sessions. So I'm Sanorita Deb. I'm doing PhD in IIT Kharagpur in the area of VLSI design. Okay, analog circuit designing is my broader area, and that's why I'm taking analog electronics here. Okay, and therefore I said that a few questions you can give me from electronic devices as well if you have doubt, but I might not be able to dig in very deep into that. Okay, but I'll try my best. Okay, so I hope this is clear now. So analog electronics questions you guys can send me and I'll just solve them in the next class. But please send them by Wednesday, okay, because I also need some time to, I have a busy schedule, so I'll just have to sit and solve those. So better if you can send me by Wednesday. Okay, so any other doubts or any other suggestions? Okay, and YouTube link I had given, I think. So I don't know how to search in YouTube, whether how you guys do it. So I'm very naive in YouTube and all those things. So I'm not very good at surfing through through these channels. So if I upload the video from next time, I'll just put the link of that video. And whoever of you are already having that, you can go and see the way I had done my gate preparation. So I had mentioned that in the YouTube videos, in first YouTube video, I think. And okay, any other issues also you can just mail it to me, any questions if you want. And I hope your preparations are going well, because I think it is only 2 months left, right? It's in Feb. So keep on preparing and don't take any stress about GATE exam. Just be cool and prepare, do some meditation and things which keep you calm. Okay, and don't mess up your health. Eat well before the exam. You need to eat well, exercise, and that's how you should prepare. Okay, so yeah, I hope you don't have any other doubts. So with this I will wind up the session. Okay, so let's wind up the sessions now. You can leave the meeting. Thank you, Chandrasekhar.